Welcome to qnawire.
To answer this question, we have to calculate what is the net force acting on the third sphere, for then calculating its acceleration. For that, we have to use Newton's second law, and I'm using the following reference frame. This is y, and this is x. They are my oriented axes. Then, applying Newton's second law to sphere number 3, we get the following. In the x direction, the net force is given by the mass, number 3, times the acceleration of that sphere in the x direction. But the net force that acts on the sphere number 3 in the x direction is composed by two forces, because the system has the following forces. So sphere number 1 is exerting a gravitational force on sphere number 3, like this. Let me call this F1. At the same time, sphere number 2 is exerting a force on sphere number 3, like this. Notice that the distance between the sphere number 2 and sphere number 3 and sphere number 1 and sphere number 3 is the same, 1.2 meters. Therefore, the force that the sphere number 2 exerts on sphere number 3 and sphere number 1 exerts on sphere number 3 have the same magnitude. So this is F12. Then, the net force that acts on the x direction is composed by the x component of both these forces. We have the x component of this force, and we have the x component of this force. Then, the net force is given by F1 component x minus F1 component x. And this is the mass of the third sphere times its acceleration. You can see that because of the symmetry, there is a cancellation in these forces, and this results in an acceleration in the x direction that is 0. Now we repeat this to the y direction. In the y direction, we have two forces acting. The y component of the force F1, and again the y component of the force F1. Then, in the y direction, the net force, which is given by the mass of sphere number 3 times its y acceleration, results in 2 times F1 component y being equals to the mass of sphere number 3 times its vertical acceleration. Notice that these components points to the negative y direction, so we have to include a minus sign here. Then, the y acceleration is given by minus 2 times F1y divided by m3. To calculate F1y, we have to get a relation between F1 and F1y. For that, we use this triangle, which is formed by F1 and its components, the y component and the x component. Notice that this angle is 60 degrees. Then, this other angle is an angle of 30 degrees. So this is 30 degrees. It means that this angle is 30 degrees. So we have a 30 degrees angle here. Then the y component is given by the cosine of 30 degrees. So the cosine of 30 degrees is F1y divided by F1. And then F1 component y is F1 times the cosine of 30. So the y acceleration is given by minus 2 times F1 times the cosine of 30 degrees divided by m3. But F1 is a gravitational force, and we know how to calculate gravitational forces. F1 is given by the mass of sphere number 1 or number 2, they have the same masses, times the mass of sphere number 3 times Newton's constant divided by the distance, let me call it L, between spheres 1 and 3 squared. Then the acceleration in the y direction is minus 2 times m1 times m3 times g times the cosine of 30 degrees divided by m3 times L squared. Then the mass m3 is simplified, and we are left with an expression for the acceleration in the y direction. And this expression is The y acceleration is given by minus 2 times m1 times g times the cosine of 30 degrees divided by L squared. Before solving this to get a numerical value, let me organize my board. And now we can plug in the values to get a numerical value for the acceleration. Minus 2 times 2.8 times 6.67 times 10 to minus 11 times the cosine of 30 degrees divided by 1.2 squared. And this results in acceleration of approximately 2.25 times 10 to minus 10 with a minus sign meters per second squared. So as the x component is equals to 0, as we have seen, then the net acceleration is 2.25 times 10 to the minus 10 meters per second squared downwards. So the magnitude is 2.25 times 10 to minus 10.